This is the video for section 8.2 on area of surfaces of revolution. So the idea with this section, again, we're in the chapter on applications of integrals, and we know how to do volumes of solids of revolution, we know how to do area under curves, we know how to do arc length of curves, and now we're going to talk about one more geometric application. So the setup is like this. I'm going to start with a curve, y equals f of x, in some range of x values, say from a to b. And I'm going to assume that this function is non-negative. And I'm going to rotate it around the x-axis to get a surface. So since I'm rotating a curve, I won't have a solid, I'll just have a hollow shell as my geometric object. So my curve looks something like this. I have a mirror image across the x-axis like this, and I rotate. Like this. Now, the simplest type of curve that we could rotate would be a line segment. And we would rotate that, and the picture we would get in that case is of course simpler. So it's obtained by taking a cone and cutting off the top of the cone. And if we label some of the quantities in this picture, so this line segment here, let's have that be length L, and then I have two radii to think about. I have this small radius here, which I'll call R1, and this large radius here that I'll call R2. And given those quantities, the surface area in the special case, so we use S for surface area, we have S equals 2 pi RL, where R is the average of the two radii. Now, if we apply that to the more general case of our surface of revolution up here, we can treat the surface very similarly to the way we treated the length of a curve in the previous section. So we would take the curve that we started with and approximate it by a small number of secant lines, like this, and rotate those. So each case, each time we do that, we get a little small version of the shape that we have over here. So there's one there, I have another one right here, and then a third one right here. So if we use those as the approximations for the surface areas, then the general surface area formula we would get can be obtained using the following formula. So it's the integral from a to b of 2 pi times f of x, so that's the curve that I'm using, that I've rotated, times exactly the function we would use for the arc length of that curve. So the square root of 1 plus f prime of x squared dx. Right. This is derived in depth in the book, and I'll let you look at that. I want to go ahead and work through an example. So the example I'm interested in is we're going to rotate the following curve. So y equals square root of 1 plus e to the x in the range, x ranges from 0 to 1. And we're going to rotate that about the x-axis. Now, like we did with previous examples, right, so my surface area formula is going to be the integral from 0 to 1, because those are my x values. And I have 2 pi f of x, which is my function square root of 1 plus e to the x, times this other square root 1 plus f prime of x squared dx. And so I'm going to figure out what that square root of 1 plus f prime of f of x squared function looks like over here on the right. So f of x is 1 plus e to the x to the 1/2 power. So f prime of x is 1/2 1 plus e to the x to the minus 1/2 power times e to the x. And so I need to square that and add 1. So that's going to be 1 plus, now let's convert this all to a fraction, so it's e to the x over 2 square root 1 plus e to the x squared. So we have 1 plus e to the 2x over 4 1 plus e to the x. So that's what happens when we square the numerator and square the denominator, and I'll combine that together into a single radical expression. So 4 times 1 plus e to the x plus e to the 2x over 4 1 plus e to the x. And I'm going to simplify that numerator, which happens to simplify quite nicely in this case. So I multiply those bits out. 4 plus 4 e to the x plus e to the 2x over that original denominator. And I find that that numerator factors. It's 2 plus e to the x squared, 4 times 1 plus e to the x in the denominator. And for problems that come in this section and the preceding section, these sorts of expressions, like we have in the numerator here, we have to learn to recognize those as perfect squares like this. Right. So now we can plug that into the expression we have here for the surface area. I'll pull out the 2 pi square root of 1 plus e to the x times the square root of that entire expression the numerator is a perfect square, and I have the denominator, so 2 pi integral from 0 to 1 of square root of 1 plus e to the x times 2 plus e to the x over the square root of 1 plus e to the x dx, and we cancel here to get 2 pi times the integral from 0 to 1, 2 plus e to the x dx. And this, thankfully, is an integral that we can actually compute. 2 pi times 2x plus e to the x evaluated from 0 to 1. We have 2 pi times 2 plus e minus, whoops, not minus up there, but minus 1. So we end up with 2 pi e plus 1 units squared, since we're computing surface area, which is a very nice clean formula for this surface area. Further examples of this type can be found in the book. So examples 1 and 3 starting on page 548. Other situations that we'll see in the text, and I encourage you to look at these, is if you take the curve x equals g of y in the range c less than or equal to y less than or equal to d, and rotate that curve about the y-axis. This is all perfectly symmetrical, so the surface area formula we would get in this case is the integral from c to d of 2 pi g of y square root 1 plus g prime of y squared dy. And you can see an example like this one, example 2, in the section. This is the end of the very short video on section 8.2, area of surfaces of revolution.